Okay, so welcome to the second day, and my presentation today will be mostly about aspects of frame theory. So in a way it will not be a new, there will be no new terminology for you, but hopefully I will try to emphasize different aspects from what you get from reading articles about frame theory. Actually, it has become fashionable to look into various generalizations of frame theory, Banach frames and so on, which I think are important, but they shouldn't consider it as generalizations on their own sake. So if we have the very concrete examples from signal expansion, here you have very concrete situations where you want to answer certain questions. For example, how can I expand a signal in a good way? When can I guarantee good convergence of the expansion? Can the coefficients be chosen in a linear way? Or how much advantage, we have yesterday have seen a little bit, how much advantage do you have if you allow nonlinear approximation, so-called adaptive signal processing. So it's not that I'm using a system, you're giving me a signal, and I'm applying my linear procedure, but I say, well, because the signal has these features, these jumps and these places, I try to use something which is taking care of this. And of course, if you do something fancy, you would not like to spend days and hours to wait for the answer. So in each case, you want to have good algorithms. And if you want to have good algorithms, it's a question not only of time, but also of other resources like memory resources. We're seeing this when we do Gabor analysis, not just for 1D, but for 2D, 3D or so. Very quickly we fall into what is called the curse of dimension. So just 2, 3 or more variables may require things that cannot be done I mean, that can easily be done in 1D, but that cannot be performed on current computers, but also very likely, if you think of 3D, not on computers in 5 or in 10 years. So it makes really a lot of sense to rather have maybe approximate dual frames for such situations, plus a good computational engine that allows you to use this auxiliary construction still to do what you want to do in terms of performing these things. Now, I'm going back first to the linear algebra situation. And I want to remind you that we have, in general, this situation, the 4 spaces. So if you give me a bunch of signals, I either put them into a matrix as columns or row vectors. So MATLAB thinks in terms of columns. I usually think of myself as a medical doctor inspecting a collection of signals. So you give me a first signal, a second signal. So for me, it's very often a system of row vectors. But as we know, it's an easy trick that you learn everywhere. The transposition, in the complex case, transposition with conjugating, maps one system into the other. So everything I'm saying to you about columns can be translated into rows and so on. Now, the question, the picture that I want to convey to you, Gilbert Strang uses a slightly different one, but it's the same idea. It's the 4 spaces, and these 4 spaces are, in my terminology, the null space of A. So how do you get the basis here? In MATLAB, an orthogonal basis, you do null of A. That gives you a collection of column vectors which are mapped into the 0 space. They're a basis. Of course, the number of the deficiency is just the dimension, usually n, minus the rank of the matrix. Here you have what I call the column space. So that's the set of all A with X. Remember that X in Rn, that applying the matrix means the vectors decides how much of the linear, how much of each column is used, x1 times the first column and so on. So the range of the linear map represented by the matrix is just the column space. Correspondingly, you have a basis, and this basis can be obtained by ort of A. So it's just in the idea, well, I give you a bunch of vectors, of column vectors, and please orthogonalize it. Make an orthonormal basis for the same space. Now, clearly, here you have the null space, and everything is symmetric of A prime. And clearly you get it a basis by applying null A prime. And then the row space, well, this is the terminology that we use for linear algebra courses. Row space is preserved under Gaussian elimination. We manipulate, we apply elementary matrices from the left that leaves the row space invariant. But it's actually then a strange question. I mean, how can I apply my matrix when I restrict it to the row space? So as first-year student coming with a row vector and a matrix, you cannot apply it. Well, it's actually the wrong viewpoint. It's not the rows of the matrix, it's the columns of A prime. So I would just emphasize that this is meant to be the column space of A prime, and then actually the picture is perfect because you have two null spaces and two column spaces from both A and A prime, and every matrix allows this. Now, it's clear that you have special cases, and I want to cover it in one case. You call a matrix, of course, a matrix of maximal rank. Maximal rank, meaning that the rank of this, so that's the dimension of either of these two column spaces. Remember, they are of course of equal dimension because they fit very well. You apply to the row space, to the mapping you get here. You apply to the column space, the A prime, you come back. So this and the pseudo-inverse is helping you to really invert it in a strict sense, not just in going back in the other direction. So, but if the minimum of M and N is the rank, then you say the matrix is of maximal rank. Note that this is a terminology which does not depend on the question whether you are having a row or column spaces. So if you have a matrix of maximal rank, transposing it, this property of course is preserved. Now what does it mean? If you have 5 vectors in R3, they should be at least as decent. There are already so many. They should at least span the space. If you have 2 vectors or fewer vectors, they are of course not spanning all of R3, but they should be at least as decent to span as much as they can. So what does it mean in this picture? Actually, I have to complete the picture. I have to tell you, we have a mapping. Let's see how we can do it. We have the mapping here, which is T, and T is just X goes to A multiplied with X, restricted to the column space of, the column space of A prime. What we know and what we have seen yesterday, that this has not anymore a null space because it has been ignored, and therefore this mapping is invertible. So it's a mapping now from the column space back to what we usually call the row space. And T to the minus 1, I'm just writing in inverse, is the basis for A plus. The pseudo-inverse is doing exactly this, ignoring the null spaces, and whenever you give me a vector on this side here, I say, well, Ax plus B cannot be solved. I'm outside, potentially outside of the column space, so please project. Then I make it consistent. I'm here, and then this way of going back is just a pseudo-inverse. So we have this, and of course also the claim that A prime, you could have a different mapping going from here to here. Yeah, you can apply. Maybe I take a different color. You can also apply T, and then you can apply a mapping called T prime, which is the restriction of multiplication with A prime to the column space of A. And you can imagine that as I draw it, these two things are not necessarily the same, but I will want to discuss it separately. Now, what are the interesting cases? So either M is bigger than N, so you're giving me more vectors. No, but you're giving me few vectors in, I mean, this is the situation that you have long column vectors. So you have a small number of column, potentially small number of column vectors. So this means the columns of A are linear independent. Linear independent. The other situation is if n is bigger than m, so you have more vectors in a smaller space, so this is the situation, I have 5 vectors and now 3, then the columns of A are a spanning system. For R, or for, let's say, complex is better, Cm. So what does it mean? We have 2 types of diagrams. In terms of diagrams, you can say either I have a mapping which may have a null space. So this is now Cn split into something, but it's mapped surjectively onto all of Cn. So that's the surjective case. Or you are having a situation that there is no null space, so this guy is the small guy which is embedded into the Cm, but there is an orthogonal complement, and that's the null space of A. So these are the 2 situations, and that's actually the situation how one should describe it. This configuration is also possible in the case of Hilbert spaces. And here I want to really spend a little bit time on emphasizing that normal standard education that you get in functional analysis is a little bit deceptive. You're getting the idea, well, in linear algebra you learn about linear independence. And then you're going into the functional analysis course, and even an infinite set is called linear independent if, taking out arbitrary many elements, you can say that the linear combination is representing the 0 vector only when the coefficients are 0. But on the other hand, I mean, when you talk about a basis, we know in an infinite dimensional space, a basis can never consist of finitely any elements. So a non-finite dimensional space requires, whenever you do signal expansion from a given basis, from a given system, whether it's a basis or a frame or whatever, you have to allow infinite representations. So it's a bit strange that you're saying, well, linear independence is only allowing to consider finitely many vectors. So one has to think about the situation of what does it mean to generalize the concept of linear independence that we are knowing from linear algebra to the infinite dimensional setting. The second question is, of course, the other one that we say, yes, when we have vectors in a Hilbert space, and now we try to generalize the system of generating sets, then of course we should not speak about subspaces only. So what does it mean a set of vectors in Cm is a generating subset? It means you're giving me any vector and I can write it as a linear combination. And we agree that there may be redundancy built in, so I may be able to provide a lot of representations. I mean, that's quite clear. When we go to infinite dimensions and people say, yes, we are not allowed to do infinite linear combinations. Well, what you can do is you can say, well, if you give me a vector and an epsilon, then I can represent an approximation to this vector within the epsilon precision. Okay, that sounds fine. You translate it and you find out, well, this means in the standard terminology, the set is total. The set is total, remember, I mean, recall the definition. A family Fi, I in I is total in the Hilbert space if you have the following. You give me any vector in the Hilbert space. You give me any epsilon, and I have to be able to provide a linear combination such that the linear combination of these vectors with appropriately chosen coefficients maybe I should say I in F for finite subset. So there's a finite subset of complex coefficients such that the approximation measured in the Hilbert space sense is less than epsilon. Okay, so good, so fine, but what if you give me another epsilon which is a bit smaller? Then, of course, the definition allows me to say, well, let's forget about the old thing and rebuild it from scratch. So it does not mean, and I want to emphasize this very drastically, not implying, so claim is, this does not implying that I can represent F as a sum of maybe using Ci tilde, Fi, I in I. Because the naive way of doing it would be or the natural way of trying it would be the following. You give me an epsilon, and you give, I find an approximation. You give me a smaller epsilon, I find another approximation. Then I'm putting myself at the position of element number 7. So I'm watching what happens at the fixed coefficients. And I would like to see that, well, the more you squeeze my epsilon, the better the coefficients will be to the final ones. And so kind of Ci, depending on epsilon, could that converge and could the limit be something like this? It will not work. A good example is need not work. And a good example is actually the very classical example of Gabor. Gabor was in the optimistic situation of saying, well, I take the Gauss function. The Gauss function is e to the pi t squared. Nice, very beautiful function, Schwarz function, invariant under the Fourier transform. Then he would say, shift operator, just to recall it, or maybe x is f of z minus x, and modulation operator is in this case meant to be the multiplication with the pure frequency omega, so z f of z. So when I tell you I modulate with frequency omega equals 3, it means I have the real part, a cosine function which has, what did I say, omega equals 3, has 3 oscillation per unit interval. That's just the standard normalization. So he would say the family could be, take the Gauss function, take the integer translates, and take the integer modulations. And in this particular case, because of these normalizations, you even can say they commute. So you can take Tn modulation by k of G0. So this family is a great family from the wrong point of view, I would say. Because, what can you say? It is linear independent. Any finite family of translates, it doesn't matter whether it's on a lattice or so, of the Gauss function is linear independent. And there's a famous conjecture, more or less going back to Topivala, and Chris Heil has propagated this very much. If you choose an arbitrary L2 function and you choose arbitrary time frequency shifted copies, whether then it also has to be linear independent. So a lot of people have tried to solve this problem. There are very good, interesting partial results. For the Gauss function, it's very easy to prove it. Roughly speaking, if you first think of the Gauss function in terms of only translates, if somebody is saying, I have 50 translates of the Gauss function, and you want to show that then if this is the zero function, then this linear combination has to be 0. The recipe is the following. So assume I'm having translation parameters over the table here. So, and the linear combination is 0. Well, the last guy sitting where I have maybe here, I have this position. I'm just going very far away. At this place, practically due to the strong decay of the Gauss function, see only the last guy. So the contribution of all other Gauss functions which are further away has to be so small, if I go far away, that the coefficient of this first guy has to be 0. Well, and then by induction, the other ones cannot be. So this is, well, it's the trick with finite dimensionality. But there exists a sequence CKN in L infinity. Actually, it's a checkerboard pattern, so it's a plus-minus scheme. So you put the Gauss function and the negative shifted Gauss function and the positive shifted by 2, and you fill the whole time frequency plane, the lattice, with plus-minus, such that the sum of, well, it's actually -1 of n plus k, something like this. Mn t, or mk tn g0 is 0. Well, it's a strange situation in the following sense, that clearly this is not a completely terrible sequence. It's bounded. What about the convergence? It's not so nice convergent, but still in the distributional sense it's converging, and what is coming out is 0. So kind of, if you are allowing reasonable coefficients, but infinite, of course, you're losing the uniqueness. So there is some trouble going on. On the other hand, it's also, this family is total. And this is exactly, but it's not a frame. I mean, but what does it practically mean? I've not given the definition still, but it means you're giving me an epsilon, I have an approximation. You're giving me a small epsilon, I have a new one, and so on. And sometimes I compare it with the following situation. Somebody tells you, well, give me your specification, I will be able to build a software for you with fulfilling all the specifications. The next day you come and say, sorry, I forgot, I would like to have 2 extra features. And you say, yes, give me another half year, I will write you a new program that's having this extra feature as well. That's stupid, we won't have upwards compatibility. So we want to have better approximation, better coefficients. And that's what a good frame is delivering to you. And now we come to the formal definition. And you should not see it as a, so you all know probably this definition. A family, I call it maybe GI, I in I, is a frame in a Hilbert space if and only if there exists some positive constant, that's a traditional setting, A and B, such that A times F squared is less than the sum of the coefficients that you get, Fi squared less than B times F squared for all elements in your Hilbert space. This is nice and okay, but it's not really important from my point of view to have this equation, but to have this diagram. And the diagram, I mean, it's now hidden a little bit. The diagram on the left-hand side, you are having you are having enough building blocks to generate every element, or either as it asked. In abstract setting, you have x goes to A star x is surjective. Atomic decompositions, or y goes to, again equivalent, y goes to y, A prime with y is injective. This is the frame viewpoint. So I'm taking you back now into the early days of wavelet theory, which has a little bit to do with CIRM, because Alex Grossman was teaching here and Mollet was not far away, and that's also maybe why I'm here. So in these days you could read, well, why do we need frames? And nowadays this is common knowledge and viewpoint. Well, because we have to deal with signals. How can we deal with the signals on the computer? Well, we take measurements, and we take these measurements. Well, how do I take measurements? By a linear procedure. If we're in a Hilbert space, how do we take measurements? We take scalar products with vectors from our Hilbert space. So the viewpoint is, in this viewpoint, Fi are linear measurements. And the frame elements are the elements describing these frame elements, these measurements, in the spirit of the Riesz representation theorem. So either you say a frame is a collection of measurements, but then of course the question is, having the measurements, how can we construct the function? This is one game. With Charlie Gröchenig in our Kobe theory, we took another viewpoint, and usually I relate it to Lego. We were using the terminology of atomic decomposition, but at the end it's not good. It's like I'm showing you a house and you are supposed to decompose it into the bricks. No, no. I'm showing you a plan of a house, so to say the architect is making something. I'm giving you a box of Lego stones and say, well, can you build this house from these Lego stones? And I don't know if your generation has played a lot with Lego, but if you're kind of a little bit smart, then maybe you say, well, I try to use first the big blocks because then it's more stable, and then later on I fill in the small ones. So somehow, I mean, even with Lego you can learn a little bit about wavelet decompositions, but that's this viewpoint. So somebody is giving you an object that you want to build, and he's telling you there is not a unique way. It's not an autonomous system where everybody knows how to build it. You just have to learn how to build autonomous systems, and it's a great business, of course, in the positive sense. It's very good if people are able to construct autonomous bases that have certain properties. But sometimes it's simply impossible to create autonomous systems, and we will see in a moment two such examples. And therefore, one has to go with some redundant families, and in these redundant families one wants to represent. And if one wants to represent, of course one wants to represent, if possible, in the cheapest possible way. One would like to have coefficients which depend in a linear way on the elements that are represented. And then we're very much back to the situation that we have here. Okay, going back to the Hilbert space equal to R2, most simple Hilbert space. And I may mention that in the very early days we also had a short discussion once saying, well, this frame concept, that's probably something infinite dimensional. Just because we were always thinking of the examples. No, no, it's something that you can explain very well in any linear algebra course. We know an orthonormal system is, of course, a frame, is a generating system. But if I show you these things, these are all generating systems for the plane. Which one would you consider as good, which maybe not so good or so? Anybody having arguments about any of these examples? I mean, we could make a voting and say, oh, well. Yeah. Yes. This, for example, I used these two to explain. You may want to have, and I'm coming of course from harmonic analysis, you may want to have a group action transporting all from one vector, all the other ones. So if you give me an orthonormal system, there is no group such that the full group action is generating the whole system. Here it's fine, I take one vector, any direction, I apply the rotation group with multiples of 120 degrees, I have 3 vectors. Here I have another advantage, the redundancy is higher, I have 4 vectors, but I can ask the additional property that if you give me any vector, I always can write a set of coefficients which are non-negative. I'm not sure if this is useful, but that would be a simple extra property that you can enforce. So what is not so good about these two things here? Which one would you prefer if you would have to use one of the not so nice ones? So let's say that's number 4 and number 5. Yes, and even if it was not an orthonormal basis, it's that the main directions are well represented. Whereas here, well, it looks as if they're going in different, well, they go in different directions, but the orientation is practically the same. So here you have almost, I mean, if you replace a frame by another vector by its inverse, so it would be more or less equivalent to this situation. yes, they are linear dependent, but how do you represent a vector which is perpendicular to this one? Well, you choose maybe the first vector, go a long way in this direction, and then you go back. Well, in the singular value decomposition, you can say, well, is this a generating system? Well, if I try to put my hand in a flat position, no, it's not. It's generating a system. Now I'm making the thumb a little bit outside. Yeah, how can, or maybe like this, so it's going upwards. How can I represent this vector? Well, I have to go a long way until this slightly flat vector is reaching the level of this unit vector, and then I take a linear combination of the others going back. So it's very expensive. That's exactly reflected here. So what does it mean to have, so the quality of a frame, is, of course, more or less B over A. We should be careful. In the definition, you say there exists some A, some B. In practice, you hope that you have knowledge about the optimal value of A and B. And as a side remark, I would tell you, without going into the frame iteration algorithm, it may happen that you have some knowledge. Somebody tells you, I can improve your knowledge. I give you a better B and a better A. And still the frame algorithm is afterwards converging not as fast. So that's because if you have, so to say, if you have two sloppy values here, yeah, so maybe, I mention only for frame iteration, kind of, well, I have to write it. It is for the inversion of the frame operators. For the inversion of the frame operator, which plays the significant role. S of f is defined as the sum of fi over the whole family. The optimal relaxation parameter, one can prove it. Optimal relaxation parameter is, now I forgot it. It's, does anyone remember it? I think it's 2 over A plus B. But I have to check it. I put a question mark and I will let you know afterwards. So it's something that you compute from this for optimal values of A and B. So the only warning I would like to give you from the practical side, because we're having a computational harmonic analysis seminar here, it may happen that somebody is giving you two wrong guesses, which maybe you could, probably it's wrong. Yeah, okay. So assume somebody gives you an estimate where the A is a little bit too small and the B is a little bit too big. Maybe it balances. So if somebody tells you or uses the argument, in order to have a good way to invert the frame operator, I have to have better bounds on these numbers A and B. That's not necessarily a good argument, because you may be in the unlucky situation that with more information, you are able, your algorithm will run slower. Because this claim about optimal speed is with the optimal values. And if you have one wrong value and one that you change, then you may lose the balance. And I mentioned it. I will try to figure out and remember the case where this happens. It's not a very deep thing, but it's an argument that I have seen very often. Okay, so what is the frame operator? Short way of explaining it. Somebody is giving you a system of vectors. He tells you, or you observe, it's not an orthonormal system. Well, still, let's try to use it as if it was an orthonormal system. And if you're lucky, then this frame operator is not far away from the identity. Actually, this very definition tells you that this condition is that A times identity is a non-negative operator is between the two positive multiples of the identity. And therefore, you can, of course, divide by B. So maybe I do it with color chalk. So I divide by B. So S over B, and you have already squeezed the operator between a multiple of the identity, which is strictly positive, and the identity. Therefore, for simple reasons, the eigenvalues have to be in that interval from A over B to 1, and therefore the operator has to be invertible. Then you can ask, well, maybe I should not use 1 over B, but lambda times S, and balance it, and then you come to this value where you have optimal control about how close a multiple of the frame operator can be to the identity. But I don't want to go too much into this. Just remembering, what is the problem here? The problem here is that A is small. This vector is, on the one hand, a troublemaker because I cannot represent it well, because in that direction I have very little information. On the other hand, if I take a scalar product of this pointed vector with all these vectors, all these scalar products will be quite small. Therefore, this expression will, for this vector f, be very small, which means the A will be small. Now, the other question is, and that's also important, why is this not so good? I mean, it has every direction, but we have here a bunch of vectors which are going into the same, more or less the same direction. Now, if I'm giving you a vector x, maybe I give you a family, maybe I'm giving you the family E1, 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 and E2. That would be something like this. 4 times the same unit vector and just the orthogonal vector. And what is the cheapest representation of E1? And the first thing that comes to mind, well, I just take E1. Yeah, which copy? Well, the first, the second, any one. No, the cheapest version is I take a quarter of copy 1 of these vectors plus all of the 4 copies. Sorry. So these are 4 vectors. Why is this cheaper? The cost is, well, in the L2 norm, 1 over 4 is a linear factor. And then I have to ask, what is the L1 norm of the vector? I've used 1 times each of these 4 vectors. So I've not used the last one, so that's this. And that's, of course, the square root of 4, which is 2 divided by 4, which is 1/2. So the cost of representing a vector in the L2 sense by having multiples of it is quite small, and therefore the more vectors you have in one direction, the cheaper you can do it. I was involved in a paper with my student Sebastian and a colleague from Greece about so-called universal series, which is just, I would say, it's an academic interesting observation. There was the notation of universal series. So what is a universal series? And the claim was it should be useful in approximation theory, which I absolutely don't believe. An universal series is a series in a vector space, or let's say can be finite dimensional or infinite dimensional, where during the partial sum process, you're adding up things, you reach almost every point with arbitrary precision. So think of, just as a, not as a plane wave, but yeah, maybe you take a plane map of Europe. Then choose 100 cities. And then you say a sequence of epsilon. So I'm coming to a distance of 1/2 to Vienna, then a distance of 1/3 to Marseille, then a distance of, and all that with an arbitrary small L2 norm. And I mean, how can this work? And the answer is very cheap, very possible. Well, if I can use arbitrary small budget to get arbitrary large distances, well, how can I do it? I want to go 1 kilometer. I spend, of course, for the first trip, I make a countable sequence of points that I have to meet. So the first trip is just maybe 20 kilometers. But I can make 20 kilometers by taking steps of so small size that the L2 norm is epsilon over 2. Then there's still infinitely many to go, but I can, for half the price of this, I can make the second distance. So it's clear that this sequence already, in order to meet the third point, I need 1 million points, partial sums. So it's completely impractical, but it's interesting because it makes this principle of you can go with many, many vectors a long distance at a very cheap price. What it also tells you, and this example is useful in its following sense, that frame theory is quite useful in many respects, but it's not good for sparsity. It's just the opposite. When you have many vectors in a similar direction, the frame solution tells you how can you balance the contribution of the individual vectors. It's very good if you have, for example, noisy data. So I remember another situation where frame theory comes in quite nicely. You have a band-limited situation on the torus. So assume that this is a band-limited function on the torus. So it's smooth. So you can say it's a trigonometric polynomial of some given degree. Polynomial. Now, we all know Shannon sampling theorems. Therefore, the interesting case is when you are having irregular sampling. Well, what does it mean? I have from this function, I have f of ti. But we also know that a band-limited function on the Fourier transform side is the same as the function, Fourier transform, multiplied with a rectangular function, which is the indicator function of my spectrum. So it's the indicator function from minus omega 0 to plus omega 0. So if I do it in MATLAB, I will say maximal frequency 12. Then I have minus 12, including 0. I have 25 free coefficients. And you're giving me, hopefully, I don't know, 35 coefficients, samples, and I try to find out what it is. Now, what we have to do here is we have to write it as sinc functions at ti, and because the sinc function is scalar product, I can say this is a shifted version of the sinc function correlated with the f. So suddenly, knowing the samples of a band-limited function is the same as knowing scalar products of these functions against shifted sinc functions. And so the question of being able to reproduce the function from the given function is equivalent to ask the question, is this family, so the question is this family of shifted sinc function a frame? A frame in the Hilbert space of all square integrable functions, or if you want, trigonometric polynomials, where the L2 norm of the coefficients is the standard scalar product. Due to Plancherel, you can do it like this. Okay. When would you expect that such a family is a good frame? So again, if I take a 25-dimensional space, it's clear it has to have at least 25 points. If it's irregular, I think it's good to have some redundancy built in. When would you expect trouble with the A, with the lower bound? When are directions not represented? I mean, which property of the point set? So remember, I was labeling, or I was pretending to label the points as T1, T2, and so on. So there are 35, let's say, points. What does it mean, lack of information in some directions in this picture here? No, lack of information. Now, when you try to do interpolation, I mean, you could do piecewise linear interpolation, but if you have a large gap, then you have no information there. So you may have a curve which is dropping down. I'm giving you a sample at the positive part. I'm ignoring the negative part, and you jump to this. You would make this straight line, but you should go down. So bad properties in the spirit of not having all representations here is, well, I'm of course trained in this business, but I have seen many examples. I would look for the largest gaps. The A has to do with the largest gaps. So if somebody is giving me data, or they are coming from a tomographic device or so, I cannot do much more, but try to make the best and be aware that these gaps have to be maybe taken care of, that they may be the reason why the problem is an ill-posed problem, why the regularization methods that we have heard yesterday may have to be applied. Now the other situation is, and now going so to say in this direction, if the gaps are not too bad, and actually we have theorems, Charlie Gröchenig has proved the theorem saying you have a very natural notion of a Nyquist rate. So you kind of divide the interval into 25 equal points, and that's the maximal distance that you expect to be the relevant size of gap size. So assume you have enough points, it's not, but assume you have a lot of points here. Then you're in this situation. The B is blowing up. Now, in some discussion, some smart colleague was saying, well, whenever you have too many points, you can throw away some points. You ignore these values. And I said, yes, correct. The best idea would be throw away the non-reliable samples and keep the reliable ones. So I'm giving you not 35, but 45 points there. Many of them are taken in this region where I have now put too many points. But how do you know? How can you tell me which one are the bad ones? Maybe this was an environment where in this region there was a lot of noise. I mean, there was kind of, the measurement was more difficult. So I was making more measurements just to hope that on average it would balance out. So it's not a good idea to say in this direction we should throw away things. But what our strategy was essentially to say, well, if you have too many points, try to make them shorter. Which is a harmless trick. It practically means if you have here this here, maybe you just multiply these numbers with these vectors with length vectors. Why? Because if you look at the frame operator, you can, it's a preconditioner, a simple preconditioner. You can make the frame better. And if you make it better by a harmless trick, if somebody tells you, I know the scalar product of f with fi, and you choose your gamma I, of course you know the scalar product with fi times gamma I, and vice versa. So if I just renormalize everything, but make my problem more stable in a good way, because here I may have good reasons to have many sampling values, but I want to have them balanced. Okay, so I tried to explain to you a little bit how you can geometrically take these things into account. Now, the next thing is when you have the full picture, so frame theory, frame diagram, is for me now the classical situation. You're giving me a family, and you claim it's a frame, or together we have verified it's a frame. Then you look at the coefficient mapping. Coefficient mapping is, in the sense of matrix, the A prime. So it's the mapping of f goes to f with scalar product with fi. Now, where is this sequence? Clearly, it's in L2. That's just a reformulation of this definition. It's in L2 of the space, and we can control is bounded plus injective. So we're saying, well, it's very good if somebody can fabricate in your Hilbert space an orthonormal basis, because once you have an orthonormal basis, the whole Hilbert space is identified with the canonical copy, which is L2. So isomorphism between your Hilbert space of signals and a prototype. Now you could say, if it's not an orthonormal system, but what people call the respaces, then you have still an isomorphism. So it's invertible, wonderful, you can do everything, convergence and all these things are preserved. I will come to respaces in a moment also. Here we are having a change of perspective. We take the function, we have a mapping which is not supposed to, which doesn't have to be isometric, that would be the tight frame case, but at least it should be isomorphic. So we're saying a frame is just, abstractly speaking, there exists an isomorphism between your abstract Hilbert space or your concrete Hilbert space of functions, of operators or so, and a closed subspace of L2. So once more, I'm just taking this picture and I'm replacing the Cn, and n in this case was the small guy, by the Hilbert space. I'm saying this hole is L2, and here I have H0, which is the coefficient mapping applied to your Hilbert space. So it's a closed subspace of L2. And why is this the same? Well, we have a formal definition, and the formal definition says I have this property of injectivity. So if you're giving me a frame following the frame definition, I would say, okay, yes, for every element, the isomorphism consists in the coefficient mapping. So I take the elements, I'm moving over to the coefficients, and they are in the right space. They are in L2. Why are they a closed subspace? You're giving me a sequence of frame coefficients and ask, well, if this is convergent, is the limit also in the closure, in the same space, sorry? Well, you have a Cauchy sequence on this side. We have norm equivalence in the definition. So I go back, I have a Cauchy sequence in my Hilbert space. It has a limit, of course, because of the completeness of the Hilbert space. I use the boundedness, and I take the coefficients of the limit, and I have a closed subspace. So in that sense, if somebody is giving me an abstract isomorphism from a Hilbert space with a closed subspace, then I would say, well, please tell me how you can describe it. So how can you get the fifth component of this abstract isomorphism? Well, there must be some linear mapping from the Hilbert space to the fifth component, or for every single component, and that has to be a linear mapping. Well, it has to be a linear functional. Well, there must be an element in the Hilbert space. So whether you are telling me you have a collection of vectors such that all together they satisfy this equation, or whether you glue them together and you tell me you have an isomorphism to closed subspace, everything is fine. Okay, so the definition is useful, it's correct, but one should not so much emphasize this as equivalence of norms, but establishing an isomorphism between the abstract Hilbert space and the closed subspace. Now, Hilbert spaces do not only allow Riesz representation theorem, but there is one more thing that you can do. What can you say about a closed subspace in the Hilbert space? Or there's a property that you may not have with Banach spaces. Again, think of this situation. If this is my closed subspace, yeah. So, to say it's an orthogonal complement means, of course, there exists an inverse mapping, a reconstitution mapping, which is going from L2 into the Hilbert space. So I didn't give this name, maybe I call this C for the coefficient mapping, such that R composed with C is the identity of this. Well, what is the mapping here? It's the pseudo-inverse. The pseudo-inverse is the mapping here. How do you describe the pseudo-inverse? As we described it yesterday. You're giving me a vector B which is not in the column space. I project it, then I'm here, and I'm going back here. So this is, once I have a projection, I can go to the range, and once I'm at the range and I have the isomorphism, I can go back. But I can also say, no, I want to have a mapping from the whole space L2. So what does it mean? Somebody is giving you a linear mapping. Of course, that is meant to be linear and bounded. Linear and bounded means that there must be some unit vector applied, and I can give this a name H or IA maybe, HI. So how is the linear mapping working? Well, it's mapping the coefficient, yeah, it's okay. The sequence X to summation Xi times HI, I in I. If you're giving me an L2 sequence, what can you say about the representation of the sequence in L2 as a sum of multiples of the vector? So X is X1 times the first unit vector plus X2 and so on. It's a sum. Well, clearly it's unconditional convergent. I can take the first, the second, the third one, but I can take in any order. Why is this relevant? Well, maybe you want to take in a wavelet system or in a frame system the double indices in some order. You may want to have a rectangular box in the frame business. You take more and more scales, more and more positions, or you take all the positions at one scale, then you add the next scale. So the order should not be relevant for the summation process. We all know the trouble that people had over this in centuries almost with LP and convergence and so on. You have to be very careful with how to sum up frequencies such that it's fine. No, I would not like to do it. Would like to behave like orthogonal systems. So we have this situation, and it's unconditional convergent. Why do I emphasize this? Because when you're going to the situation of Banach spaces, the first natural attempt to generalize frame theory to the Banach setting would be to say, okay, what are the players here? I was telling you we have a Hilbert space and we have a prototypical Hilbert space, which is L2. So maybe if we go to the general situation, we should allow other sequence spaces. What are the next after L2? LP spaces, for example. So maybe we find situations where you have a Banach space and the mapping is such that the norm in the Banach space is the same as the LP sequence of these norms. Well, what is a good example here? I could take the LP spaces and replace the L1 norm by the LP norm. And then you can say, well, maybe if you do regular sampling, the sampling LP sum is hopefully an approximation to the LP norm of the function. So the main point is when you generalize it from p equal 1 to general p, that you should be able to prove another norm equivalence. Here I have to give several warnings. First one is a generalization which says, for every p in some range, one can do such a thing, maybe not so useful. Why? Because typical situation, and especially when you really use the sinc function, that will happen. You are not allowed to have, you cannot have it in the L1 sense. The sinc function, I mean, now I'm thinking of here the sinc function, of course, is in L1 because you're in torus. But if I switch to the real line, non-periodic case, the sinc function is in every LP, but not in L1. Why? It's also clear it cannot be in L1 because the Fourier transform of every L1 function must be continuous. But the Fourier transform of the sinc function is the rectangular function. It's clearly discontinuous. So that's clear. It cannot be in L1. Positive statement, yes, it's in every LP. So if you would do irregular sampling in LP and you have a theorem of the following type, for every P there is a pair of constants AP and BP. First of all, they may depend on the P. Secondly, if some user is providing you with data, you say, thank you for the data. I have now the knowledge that at the points Ti, over a whole family of points, nicely spread out, the sampling values are f of t. But please give me the extra information. What was the LP parameter from which you did the sampling? So did you sample a function from L5 or L12? he will look at you and don't know what it means, and it's really a ridiculous question, because you should not make use of the parameter. You should rather have an algorithm which says, yes, I can reconstruct your data. If you're giving me data from L2, the algorithm, typical an iterative algorithm, should converge in the L2 sense. If you're giving me functions from a weighted LP space, without knowing it, my algorithm should behave in such a way that the convergence is happening in the weighted LP space. So actually, I run my algorithm and observe that because I see it's convergent, it's a Cauchy sequence in the weighted LP space, the data must come from originally from a function which is in the weighted LP space and is band limited in addition. So kind of, this is to some extent a psychological thing, but I think it helps a lot to understand the situation. What is the knowledge that one requires when one is applying this theorem? And it's not an individual, but usually I say it's a situation where you would like to have good knowledge. Maybe since I'm not so much going into this, into using the computer, I maybe better use more light here. I want to tell you another situation. Now I'm switching from frame theory to respaces. So a typical situation for Ries sequences, and the modern terminology that came out in the last few years is Ries basic sequences. So later on you will, just to learn it or to emphasize it, we will talk about the Ries spaces as something that allows to have an isomorphism between your Hilbert space, the whole Hilbert space, and the L2 space. If you have a Ries basic sequence, it's like, this is a Ries basic sequence in R3. It's a linear independent set generating a linear subspace. So a Ries basic sequence is by definition something which allows me to have exactly this situation, but now with a synthesis operator. So there exists constants C and D positive, such that either you are taking coefficients in the L2 sense, and you're measuring them in the L2 sense, or, yeah, so I have to give it a name. AHI is a Ries basic sequence. If the vector that you create by doing synthesis with this vector, I in I, and take the length of this vector in the Hilbert space square is comparable, sorry, with the squares, to the original length. So it's more or less, whereas here the yellow part of the right hand was using the A prime to have such a diagram, now it's the A, really the system of columns, and it's the correct generalization of linear independent. Maybe, yeah, note. This is the same as the Gram matrix, which is, yeah, a format cardinality of A cross cardinality of I is invertible, or let's say, yeah, Gram matrix is invertible on L2 of the index set. That's another way of verifying it. So this may be an infinite matrix, but it's bounded and boundedly invertible. What can you do with an invertible matrix? You can actually invert it. It's a symmetric matrix. And now, again, just think of, I don't know, 5 vectors in R12. Somebody is giving you 5 vectors in R12. The Gram matrix gives you all the scalar products of these 5 vectors among each other. So it's a 5 by 5 matrix. I'm telling you that some 5 by 5 matrix is invertible. It's a symmetric matrix. Well, the inverse is again a 5 by 5 matrix. How can I use these rows or columns, they are the same, of this symmetric inverted matrix? Well, I can use them to say, well, I'm using, for example, the second column to fabricate from my 5 vectors a new linear combination. Exists and can be used. to fabricate the biorthogonal, the unique biorthogonal system in the with same span. So once more, first the test is a system a Riesz basis? And you think of, well, is it linear independent? If you have two vectors and they're linear independent, they're spanning a plane. I can easily find out that I can take the biorthogonal construction that I had in GeoGebra yesterday and find a biorthogonal system, which is a system of another, now in my example, 5 vectors in R12, which are such that, so recall, what does it mean? Biorthogonal, so recall the definition. Hi tilde is a family with the same index set, is biorthogonal to a family Hi, I in I, and if, of course, the scalar product of Hi tilde with Hj is just delta Ij, the Kronecker delta. So you're pairing it, and you're finding out, yes, they are satisfying this. So if you're giving me a vector x, which is a sum of a linear combination of this, how can I pick out the coefficients with number I? I just say that x with h tilde number k, and I use the biorthogonality, and I'm getting exactly the coefficient which belongs to this number. I mean, that's the usefulness of this thing. So biorthogonality is a concept, and it can be obtained by looking at the Gram matrix. And of course, again, the Gram matrix is, if it's invertible, it's a positive matrix, and it has a condition number, and the condition number is more or less the quotient of the two things, the A and the B. Now, I want to erase things. Yeah. Yeah, maybe I continue here. I've told you yesterday that when you have now a system which is a basis, and you are interested to get an orthonormal basis, Gram-Schmidt may be not the only and actually not the best choice to do the orthonormalization. Why? Because if I would have put 5 vectors on the table and would ask you, please do Gram-Schmidt, and I really think you have a basket with numbers and there are the vectors. I mean, everybody would choose a different order. You choose 1, 2, 3, 4. I choose 1, 3, 4, 2, 5 or so. And everybody is getting a different orthonormal system. If, for example, I would take a system of, example here, a system of B-splines. So these are, cubic B-splines for me are just convoluted. So this basic B-spline, and we will do it later on MATLAB, not today probably. It's the convolution power of order 4. So you can also say it's obtained by doing first the convolution of the rectangle of the box function, which itself, which gives the triangular function. Another one is triangular function, convolving it 2 more times, increases, of course, the smoothness. So we all know that the step function is having jumps. The triangular function is continuous but not differentiable. Convolving once more, it's getting differentiable but not 2 times differentiable. And when we want to do cubic splines, we have a C2 curve. Again, side comment for when you do teaching. Why are you interested in having C2 curves? Or what is the curvature? What is the second derivative? I mean, assume you have a street which is like this. Assume you have a roundabout, which in English is a roundabout. In German, it's a Kreisverkehr. A roundabout is something where you try to smoothly drive around. I like most of the French and especially British, New Zealand, and so roundabouts. They are good. Unfortunately, in Austria, they are really making something like circles. So when you're driving here, the curvature is like this, for example. What does it mean? The curvature is how I have my steering wheel. To have continuous thing means I'm not like a toy train. A toy train has straight tracks and then fixed radius. So that would be, this is also like I'm turning right, left, right. Smooth C2 means smooth change of things. I'm an elegant way of driving around these things. So you can imagine this means just I can produce smooth curves with these B-splines, and that's the regularity that is reasonable. Anything which is more can be nice, but it's not really paying off. You cannot make big differences. But it's not, it would not be good to build streets which are only C1 or so. I mean, that's what I wanted to mention. Now, why did I give this example? That these elements are general examples of Ries-basis. So there are a Ries-basic sequence, and you have seen all this in. And this Ries-basic sequence means that formally you have this definition, but also that you can find out there is another system, psi and tilde. So I have a bunch of an indexed family of functions such that it's a Ries-basis. Now to say that there is a bi-orthogonal system means a priori I have an opportunity to find a bi-orthogonal system which is in the linear span. So there is a sequence of functions. Whenever I choose an n, I find a linear combination of these shifted functions, of these shifts of these B-splines, such that this new function family is a bi-orthogonal system. But then, of course, you look a little bit closer either into the Gram matrix and observe, oh yes, this is a convolution matrix or a circulant matrix, or you use the invariance properties of these systems and find out that it's Tn of some psi tilde, which is much more interesting. And then there are formulas which I don't give now of how to compute the function. So in principle, yeah, I should give you an idea. The psi and tilde is described on the Fourier transform side. So on the frequency domain, it's something that you say, well, the Gram matrix has to be described, and you're taking the psi hat of omega. So in our case, psi would be the Fourier transform of the forced convolution power of the rectangular function, which is sinc. So it would be just sinc to the forced power. So it's a non-negative function decreasing like x over the force. So it's a bump with some small side bumps. It's a relatively harmless function. And then you have to divide it by a periodized version. So I also write the sum of a decay of psi hat absolute squared of omega k over the integers. So you take this function psi hat squared, you shift it around, make it periodic, you get the periodic function. Well, of course, the request that you have to make is that this should be never 0. And you can imagine that by rescaling or so, you always can reach such a condition. I don't want to have this. So the general theory says, if you give me any function psi, then you can do this procedure if there is no 0 here. That's all you have to do. And then on the Fourier transform side, you have a description and you have this property. Now, what about LP theory? Furthermore, maybe. We're now in the situation that we have a bi-orthogonal system for a closed subspace. So it's clear that not every L2 function is a spline function. If you are giving me a projection, if you're giving me a function f in L2, and you're asking me what is the best approximation by the elements of the closed subspace. The closed subspace is the set of all linear combinations, well, infinite linear combinations with L2 coefficients with this respect to the system. Then I would tell you, okay, what you have to do is you you have to use the bi-orthogonal system, psi and tilde, and our system is already this, but this is the same as f with psi, t and psi tilde with psi, with t and psi. Now, this is the orthogonal projection. Summation is always over the integers. But this function here, the B-spline is in the normal way, if I take the box function symmetric around 0, so from -1/2 to +1/2, the psi is symmetric, therefore the psi tilde turns out to be symmetric. So I can artificially put a flip here, so it's really nothing else but psi tilde at the position n. So the way how to indicate how one can implement it efficiently is the following. I take f convolved with psi tilde, sample it at n, and I sample this function of, I put the form this function here and convolve it, so this is maybe to be careful, and I convolve it now with the psi. So you can imagine that this can be implemented efficiently because first you have to convolve f with psi tilde, but you do it of course on the Fourier transform side. On the Fourier transform side you have already a harmless description of this psi tilde. So you can do this, then you sample, and after you have sampled it, you do again a convolution. So a few Fourier transforms allows you to do this description. Now the point is, this is an orthogonal projection in the L2 case, but what can we say about P different from 0? Different from 2. And there, again, the warning is, you should not start thinking individually. It's not a problem about L4 or L12 or L17 or so. You could argue, and if you have any knowledge, tell me so, that yes, there is uniform convexity of all these LP spaces except for P equal 1. So maybe you can prove that there is an optimal representation for a given P. I've never seen such algorithms, or at least not at work. And it's not meaningful because it depends then on the P, and actually I think it will depend in the practical sense very little on the P. What you have to ask, I'm provocatively writing it, the right question. Having the result for P equals 2, does it extend to all the LP cases? And I have not much time and I want to only mention it. The answer is yes. And what do you need for this purpose? You need using some function spaces. So I'm trying this semester here to put emphasis, different emphasis on different topics that I want to develop further or summarize. So the conference next week will be mostly on function spaces, and that's a business that I was doing for a long time, but not, at the beginning out of fun, just to understand the principles of how to construct function spaces, but then more and more to understand which spaces should be used in which place. So for example, here I'm using the situation that the psi should be in C0L1, the Wiener amalgam space, and I'm giving you only a pictorial definition of the norm. So if somebody is giving you a function on the real line, and you can easily imagine how this works in 2 dimension, then you would say, well, it may be Riemann integrable in the sense of absolute integrability of upper Riemannian sums. So it means the summation of f times indicator function of n to n plus 1, and in the general setting it would be cubes in Rd, of the subnorm. This should be finite. So this is a definition of this. And then what you have to do is show then that in this construction you can prove that also the psi tilde is in the same space So essentially what you can say is, well, it's a primitive form of atomic decomposition. You can say the elements of this space are there forming a Banach space, can be completely controlled if you know what happens to functions which are living in one of these cells. So if you know what the function is doing, if it's bounded, living in a box of size 1. Well, if it lives in the box from 5.5 to 6.5, we have 2 little boxes. If you're having infinitely many, you're adding up and you're using just more or less triangular inequality. So when you want to know, for example, somebody giving you LP sequence in set, or set D in the general case, and you want to do a summation of CK of TK psi, then you would expect that you can control this. Actually, I would prefer to control it in the norm which I call C0LP, so that would be I'm measuring local with the subnorm again, but instead of just taking the global L1 norm that I'm using here, I've taken the LP norm. I can control this by a constant, which has to do a little bit with the geometry, but not much with the individual function, times the LP norm of this function, so that's LP, times this psi norm in that amalgam space. Well, why is such a norm useful? Because if you have convergence in this sense, it also means LP plus uniform convergence. So whenever I see results, for example, about reconstruction from band-limited function, then people usually say, we have an algorithm which is convergent, first in the Hilbert space, secondly in LP spaces. But in addition, it's also convergent in the uniform sense. I'm usually saying, well, probably people should look for the convergence in this space, because once you have convergence in this space, it's also convergent in LP, because LP is LP, or in C0, which is W C0. Everybody can recognize that on an interval, the bounded continuous functions are clearly LP, so this is larger. And on the other hand, everybody knows that little LP is inside C0. So you already see how I'm using these amalgam spaces. They have a local component, a global component, and so on. Okay, now, because this is the second part which will be recorded, and I have still a few minutes, and I really want to cover one topic. It's now really jumping ahead. I'm erasing this blackboard. No, I take this one. I want to tell you how this definition of Banach frames can be extended to what I call Banach-Gelfand triples. I'm not sure how much I can tell about this in the remaining talks, but it's a setting which I find quite useful. So far, the message should have been, frames are not things with inequalities, but things that allow you to have diagrams. Well, diagrams can be done in many, can be between Hilbert spaces, the prototypical Hilbert space L2, and the abstract Hilbert space. When you're going to Banach spaces, you can do it in the Banach space setting, but actually I would like to have it for families of spaces. So, and the minimal family is of course a triple. So I'm saying like society is built on family, father, mother, and little child. I'm doing now a short course on, very short course on Banach-Gelfand triple. So, and there's actually a specific Banach-Gelfand triple, which is relevant for, not only for time frequency analysis, but it's S0, space S0, L2, and S0 prime. Everybody knows L2. S0 is the Siegel algebra. I'm writing it for RD now, which consists of all functions from the Hilbert space, such that the short time Fourier transform is integrable over R2D. So think of the nice pictures that you have seen at the very beginning of the last lesson. This spectrogram is this here. So what is the definition? Vg0 of f at the point x and omega is trying to tell you which color you see at the point in the time frequency plane. And the color is the absolute value of this function here. It's this correlation between the individual function and the G0, which is the Gauss function, put into this position. So I shift it to time t and modulate it up to frequency omega. So if you would think of this as a sound object, I would say yes, D is a short Gabor atom. It's at some time, there was some frequency, short building block. And I'm testing all these color products that I have here. Now, this space can be shown to be a Banach space with respect to the zero norm, defined as just the L1 norm of this short-term Fourier transform. So it's L1 norm of R2D. And then one can prove that, for example, this space is Fourier invariant, and we'll tell you more later on, so to say. But also, all the LP spaces are in between S0 and S0 prime. Actually, you can characterize S0 prime as the set of all temper distributions. So how can you find out whether a temper distribution is in S0 prime? And the answer is very easy. For any temper distribution, you can still define the spectrogram, just dualities, sigma applied to translation time frequency shifted Gauss function, and where this is a bounded and continuous function over R2D. Yeah, what is the norm? Of course, well, the S0 norm of sigma is equivalent to the sup norm of this spectrogram. Sup norm. Okay, what is a morphism between Banach-Gelfand triple, or for example, a morphism? Yeah, well, another example. Sorry, I should say. What is the prototypical example? Prototype is L1, L2, L infinity. I have a Hilbert space. I have a small Banach space inside the Hilbert space and the dual space, and they're having, I usually think of father and mother, in the middle the beloved child, which is the Hilbert space, that's favorite. We start very often with the Hilbert space and find something inside. Or via Fourier transform, I mean, if this would be over the integers, I would tell you, okay, there are objects which have Fourier coefficients in L1 or in L2 or in L infinity, then I would be talking about A of t, the algebra of absolutely convergent Fourier series, or L2 of the torus, or the objects which have bounded Fourier coefficients, L infinity, which usually are called pseudo-measures. They're a little bit more than measures, so they're harmless distributions. Well, that would be another Banach-Gelfand triple isomorphism. And so morphisms between such pairs are, so it's from B1, Hilbert space 1 and dual space, into B2, Hilbert space 2, B2 prime, would be, of course, such that it's linear and bounded into B2, linear and bounded. Well, the Banach space should be actually be dense, so it extends such that the Hilbert space is mapped into the Hilbert space. By duality, normally we would say B2 prime, B1 prime is mapped into B2 prime, plus, and that's very important for me, this is boundedness in the sense of norm topology, but it should be also weak star to weak star convergent. Okay, and then we have the following definition, or maybe a theorem. Where this standard diagram is used in combination with Banach-Gelfand triple. Assume, and we will do computation on this, that G lambda, lambda in lambda is a Gabor frame for the Hilbert space H, which is L2 of RD. You should imagine that this means I'm moving around in time-frequency plane, building blocks, for example, a Gauss function along a lattice. So this is a lattice. It's something of the form A, an invertible matrix applied to the standard lattice set 2D. Can be dilation, can be rotation, anything. With good quality of the G, it should be just S0. You can take any Schwartz function, any summability kernel from classical Fourier analysis. Then there exists a G tilde, and it's also in S0. And the mapping, well, you give me the F from any of these spaces, good quality S0, general Hilbert space L2, or large space of distributions, to scalar product in a generalized sense of F with G lambda tilde is defining a retract from maybe I do it in a different way, is defining a frame mapping, a frame coefficient frame mapping from, you can choose S0, L2, S0 prime into, well, what is the corresponding sequence spaces? Of course, L2, L1, L2, L infinity. And if you do approximation in the weak star sense here, you get point-wise, coordinate-wise convergence here, which is weak star in L infinity, such that the reconstruction can be performed R. So somebody is giving me a sequence C lambda. This sequence can be L1, L2, L infinity, and of course by interpolation you can do LP cases or so, such that R, which is given by this is mapped to the sum over C lambda, G lambda, lambda in lambda. I don't write down because I don't have much place. Of course, this is unconditional conversion, so you can do the summation in any order. You can take first the big ones, the big coefficients, and the small ones. So that this is going back satisfies the condition that we had, R cross C equals identity. For every, I mean, I'm putting a star here, whatever you put here. So you have synthesis, but you don't have to restrict your attention to the Hilbert space. So the main message here is, well, around the Hilbert space there is a family of objects. And the reconstruction is not just restricted to the Hilbert space case, but it's possible in general. Another thing which I forgot to mention, at least I want to mention it at the very end, is why is the upper part of this diagram that I have erased now so important? Because when you're working with frame coefficients, you're starting to manipulate the coefficients. So what if you would have only the isomorphism to the range of the frame coefficient space, and then you're doing soft thresholding, hard thresholding, you say the small values should not play a role in MP3, you're discarding, due to the masking effects, the coefficients which are very close to much larger coefficients or so. These are all operations that, of course, you can do in a solid sequence space like L2, LP, or so on, but you cannot do it in the range of the spectrogram. So that's why it's important that if you have spoiled your coefficients due to noise, due to operations on the coefficient level, that you are coming back and have the reconstruction properties nevertheless. And of course you would like to have stability in all directions, but this is not the time to discuss this here. So I think I will come back to this in the next courses, and I think the next one will be more computational, and then I will also show some MATLAB on this. Thank you very much.